Let's talk about implicit differentiation, but really quickly, let's discuss Leibniz notation. So this is the standard way of writing derivatives, and this is how it works. If I have a function y that is something in terms of x, the derivative of y with respect to x, meaning this is the variable that's undergoing all the processes of differentiation, which we would normally write as y prime, or y prime of x if we wanted to be precise, will be written in Leibniz notation as dy over dx. This is a very intuitive notation because it resembles this delta y over delta x, which we use for rates of change as early as algebra 1. However, it's not exactly the same because remember, the definition of a derivative has a limit in it. So this isn't exactly a fraction, but is basically the ratio of two infinitesimals. Now, this can be written in several ways. This can be written as d over dx of the function itself, so d over dx of something done to x. These two expressions are equivalent, and this also is a very intuitive way to show chain rule. Let's go over chain rule once again. Let's imagine that my function is equal to 3 ln x plus 1 over ln x, right? I'm going to rewrite this function y in terms of a new variable called u. I'm going to say u is equal to ln x, and therefore y is equal to 3u plus 1 over u. Now, we have a very obvious application of chain rule here. So we have an outer function y and an inner function u. So what does our chain rule tell us that we'd write? Well, in the way that it was written last video, we'd say that the derivative of this whole function is going to be equal to y prime of our input, which is this outer function u, times u prime. Now, let's rewrite this in Leibniz notation. So firstly, we have the derivative of y with respect to u, which will be written as dy over du. Secondly, we have the derivative of u, and this is implied to be with respect to x, times du over dx. This might be slightly confusing. This is the correct representation for the derivative of this overall function, and it might intuitively look like we are cross-canceling du to get dy over dx. However, it's important to note that since these aren't actual fractions, they simply resemble them, we cannot cross-cancel like this. So this is equal to dy over dx, but that is because of our chain rule. But this is the standard notation of writing derivatives, so it's important that you familiarize yourself with it. Now let's look at implicit differentiation. Some functions or some relations are written in terms of both x and y, like this equation of a circle, where it's x squared plus y squared is equal to r squared. I'm going to say it's 1 for simplicity's sake. Let's say we wanted to find the derivative of this. Well, firstly, we could isolate y by moving it to that side and square rooting the whole expression, but that's a lot of work. We can simply use implicit differentiation, where we assume that y is actually some function of x. And therefore, if I have some function done to y, I'm going to call it a of y. Its derivative, so instead of using prime notation, I'm going to say d over dx of a, so its derivative with respect to x, is going to be equal to dA over dy times dy over dx. And let's see what this means for our function here. If I wanted to find the derivative, first I differentiate both sides. So I take d over dx here, and I would take d over dx on this side. Remember, derivative of a constant is 0. So this cancels out to 0. And so we have 0 is equal to this side right here. For x, it's easy. The derivative of x squared becomes 2x. And now for the y term, we first take dA over dy. So the function a simply takes y and it squares it. The derivative of that with respect to y is simply 2y. So it becomes 2y. And now we multiply by dy over dx. Now, we don't know what dy over dx is, so we can solve for it. All we have to do is isolate this term, and we'll have found our derivative. So once we do that, we get dy over dx is equal to negative x over y. And this is our derivative in terms of both x and y for our circle here. This means that if we had the point, say, 1, 0, the derivative of that would be negative 1 over, since we can't do negative 1 over 0, we're going to say it's the limit as x comma y approaches 1, 0 of f of x. It's going to be limit as y approaches 0 of y. and therefore that's going to tend to negative infinity, which means it is a vertical tangent slope at that point. Because remember, the slope of a vertical line is undefined. Let's do one more function. This one is equal to 3x plus 2x squared y squared. Now, we use the exact same process. You just take the derivative of both sides. Constants become 0, 3x becomes 3, and here we must use product rule. I'm going to take out the 2, and now remember, this becomes f prime g plus g prime f. So I'm going to start with f prime, 2x times g, so 2x y squared, plus, now g prime, we use the same process. This becomes 2y times dy over dx. So plus 2y dy over dx times f, so times x squared. Now all we have to do is once again solve for dy over dx. And that becomes 3 plus 4xy squared plus 4y x squared dy over dx is equal to 0. And therefore minus 3 minus 4xy squared divided by 4x squared y is equal to dy over dx. So if I had a point x comma y and I wanted to find the derivative or the tangent slope or any sort of rate of change at that point, I would have to plug in the values into this expression. As a result of chain rule, whenever we see some function of y, we can simply take the derivative as we would with any other variable and then multiply it by dy over dx. I shouldn't combine notations, multiply this by y prime of x. So this makes taking derivatives in terms of x and y really easy because we can just use this trick here, or saying that, dy over dx times dA over dy. Let's do one last problem. Let's suppose I have the function x squared plus xy plus y squared is equal to 27. Now, it says to find all vertical and horizontal tangent points. Now, this shape is tricky. Because we have this xy term here, it's a rotated conic, so it looks something like that. We have to find the vertical tangent points, and remember, the slope of a vertical line is undefined. So we have to find where is the derivative over dx, undefined, and we have to find the horizontal tangent points. That means where the derivative is equal to 0. To do that, let's first differentiate both sides of this function and find the derivative. So this becomes 2x plus, once again we have to use product rule, so that's 1 times y, plus g prime f, plus x times dy over dx, because remember, the derivative of y just becomes 1 times dy over dx, plus 2y dy over dx is equal to 0, because the derivative of a constant is 0. Let's solve. 2x plus y is equal to minus x minus 2y all times dy over dx. I just factored it out. And now 2x plus y divided by minus x plus 2y is equal to dy over dx. So this is our derivative. Now we just have to find wherever this is 0 or undefined. Now to find where the derivative is 0, all we have to do is find where the numerator is 0. And therefore, we're going to turn that into 2x plus y is equal to 0, y is equal to negative 2x. Now, we don't actually know what point this is yet until we plug it back into the function. So let's do that right now. X squared plus x negative 2x plus negative 2x squared is equal to 27. X squared minus 2x squared plus 4x squared is equal to 27. 3x squared is equal to 27. X is equal to plus and minus 3. So there are two solutions to this. The first solution, where our slope is 0, is that x is equal to positive 3 and therefore y is equal to negative 6. Our second solution is that x is equal to negative 3 and therefore our y is equal to positive 6. Now we have to find where our derivative is undefined, and let's clear up more space for that. So you can still see the derivative. Wherever the derivative is undefined, the only way this function can be undefined is if our denominator equals 0. So we're going to say negative x plus 2y is equal to 0. Now, because 0 is neither positive nor negative, this doesn't matter. So therefore, I can say x is equal to negative 2y. Once again, we can simply plug this back into the function to find where those points actually lie. So if we have x squared plus xy plus y squared equals 27, I'm going to plug in negative 2y wherever I see an x. So negative 2y squared plus minus 2y times y plus y squared is equal to 27. And if you'll notice, this is the exact same equation that we had earlier. The difference is x and y are swapped. So now when I solve this down, I'm going to get y is equal to plus or minus 3. And that means our solutions are either y is equal to positive 3 and x is equal to negative 6, or y is equal to negative 3 and therefore x is equal to positive 6. And so these are the solutions to our problems, with these being the horizontal tangent line because the slope is 0, and these being the vertical tangent line because the slope is undefined.